Okay, let's solve this question. We have a water tank with height of the water h inside the tank, and there is a pipe with the length of L connected to the bottom of the tank, and it has an angle theta. Water strikes to the ground with the shape as you can see, and the highest height of the water stream is h. So the question says determine the distance h as a function of theta. So determine the distance h as a function of theta. Okay, let's see how I'm going to investigate this question. I need to find a few points which I have information, or I want to find information about them. The first and the easiest selection is going to be a point at the surface of the water over this place in the tank, and I'm going to call it point 1. Why? Because the pressure is atmospheric pressure 0. Elevation, I know the elevation there, the height. Velocity is 0 because we have this assumption whenever we are talking about tank, we are talking about very large tank, and the speed of changing the level is going to be almost 0. So this is one of the points I need to have. Then I can find again another point which have a lot of information about it. The other point I'm going to select is going to be at the end of the pipe. So end of the pipe is going to be here, point 2. Why? Because I have pressure there, because this is the point liquid is in contact with the atmospheric pressure, so the pressure is going to be 0. Velocity, I don't know. Elevation, I know. So the only unknown for point 2 is going to be just velocity. Okay. What else? I need to include one more point to have this h in my Bernoulli equation calculation. So because the question says find that h, so question forced me to use this point as my third Bernoulli equation point to write the equation. Okay, so very good. Now I can start writing. So let me write the information I have. P1 is 0. V1 is 0. And Z1 elevation. Now I need to make decision. Where is my Danton? So the easiest one is going to be to consider 0 here. So this is Z direction, and Z here is going to be 0. So because of this selection, Z1 is going to be capital H. Now I have all the necessary information for point 1. Point 1. Point 2. Let's see what information I have for point 2. P2, again 0, atmospheric pressure. V2, I don't know. I need to calculate that. Z2, I know that. It is going to be sine of theta times L. So L sine of theta, which is this distance. This is going to be L sine of theta. Okay. So I have information, the necessary information for point 2. Now let's write for point 3. Okay. Pressure at point 3 is 0, again connected to atmospheric pressure, nothing there. V3, okay, we don't know. And Z3 is the elevation h. Again, we need to find this h in terms of theta. Okay, let's write the first Bernoulli equation formulas. The first one which I'm going to write is going to be between point 1 and point 2. Okay, so P1 divided by gamma plus V1 square divided by 2G plus Z1 must be equal P2 divided by gamma V2 square divided by 2G plus Z2. Let's plug the available information we have. This is going to be 0, 0, 0. So the left side is going to be just h, right side is going to be V2 squared divided by 2G plus L sine of theta. Therefore, V2, the velocity at point 2, is going to be 2G h minus L sine of theta. Okay, this equation is very familiar for us. Remember, for any jet, we said velocity of any jet is square root of 2g times the height we have. Here, the height we have is h minus L sine of theta, which is going to be this height, h minus L sine of theta, which is exactly the formula we had for jet. Okay, so we found V2. I need to clear something here. When water exits point 2 and passes point 3, the velocity we have, let me draw here, So this is the velocity at point 2. Let's call it v2, and it is going to have this angle theta. The horizontal component of this velocity, I'm going to call it v2x. I know that we don't have any acceleration in x direction. It is 0. The only acceleration we have is due to gravity. Therefore, velocity at point 3 is going to be equal the horizontal component of velocity at point 2, which is going to be v2 cosine of theta. Okay. Now we have velocity at point 3. Let's write Bernoulli equation between point 3 and 1. So P3 divided by gamma plus V3 squared divided by 2g plus Z3 is going to be equal P1 gamma V1 squared 2g plus Z1. Let's get rid of the 0 term. This is 0. This is 0. This one is just h. Also, this one is 0. Okay, this one is h. Let's put the values, and h is going to be equal v3 square divided by 2g plus h. I already found what is v3 here. So v3 is going to be v2 cosine of theta. Let's plug the number. So v2 cosine of theta square 2g plus h. Okay, I know the value of the v2 here. So let's plug that v2 here. So this is going to be 2g h minus L sine of theta times cosine of theta, cosine square theta divided by 2g plus h. So we cancel 2g's, therefore small h is going to be h, because the question asks for the height of the water at point 3. So I'm writing everything in terms of the small h. 1 minus cosine square theta plus L sine of theta cosine square theta. Okay, I know that 1 minus cosine square is going to be sine square. So let's write that. Therefore, h is going to be h times sine square theta plus L sine cosine square theta. Okay. Okay, we found the formula. Let's make it a little bit to include every part. Let's see what are the interesting information we got from h. If theta is equal 0, what happens to h? If theta is 0, the first term is going to be 0, the second term is going to be 0, so h is going to be 0. So basically it says if the pipe angle was 0 or horizontal, the h is supposed to be 0, which is correct. If theta was 90 degree, what happens? That small h is going to be 90 degrees, sine is going to be 1, cosine is going to be 0, so the second term is going to be 0, the first term is going to be 1 times h, so h. So if theta was 90 degree or vertical, the height of the water supposed to be exactly the height of the liquid, which is again correct. Okay, I hope you learned something from this question, and see you next time.